Okay, what we're going to focus on is actually graphing some transformations here. Those can be a bit tricky. The very first thing we have to realize is what's the original function we have. And what we mean by original function is this is a sine function. So if I was to graph y is equal to sine x, what would that original look like? I'm going to actually write those in because we talked about those 5 coordinates being really important. So one of them is 0, 0. Another one, let's see, this has 2 to it. So we'll say this is 1 and this is 2, okay, since they didn't give us any y coordinates. Another coordinate here is, so actually write them on the side so we don't get too bogged down on the graph. Another important coordinate is pi over 2 and 1, okay. The next one we pi and 0, which would actually be down here. Then we get 3 pi over 2 and negative 1, and then finally 2 pi and 0 again. So this is the negative 1, negative 2, and then back to pi. So here's the period of the original sine wave. Okay, and what we'll do is we'll show each transformation as we go through it. So the very first one is, if we remember, and I'll write it out again, we have y is equal to a, in this case it's sine, we'll see if there's a b variable a part of this, x plus if there's a horizontal translation, and then finally d standing for vertical translation. So we'll see which of these we have. In this case we have a, so that's negative 2, and it looks like we have a c value. C value is 10, okay? There isn't a value here. In this case, that means b is defaulted as 1 and there's no change, and there's no value added on the outside, so d happens to be 0, and that also means no change to that. So we don't have to worry about b and d in this case. But we do have to worry about a and c. So I'll actually apply the vertical stretch first because it's a positive number, so a happens to be negative 2. It gets stretched, but is also flipped because it's negative. So not only, so we'll do 2 movements here. Just a normal stretch would cause these y values, not the y values, to all be multiplied by 2. And now remember the y value here is 0, so that doesn't change. But this y value being 1 gets moved up to 2. This y value is 0 again, so I go back. This y value is negative 1, so it becomes negative 2, and then back to the original. But now we actually have a negative 2, so that means everything gets flipped. So it's actually down here. Now I know I'm using the same color. The zeros stay the same, but the max and the mins happen at different occasions, okay? So the other 2 are our old ones here. We'll do a little highlighting in blue to say this is our current version, okay? And then the last thing we have to do is move it by 10 degrees. Now this happens to be in radians. So to convert something from degrees to radians, we take the value and we multiply by pi over 180, okay? And that's actually going to give us pi over 18, I believe, once we break it down. So it's a positive value, so that means this whole thing has to be shifted pi over 18 units to the left because it's positive. That's a pretty small value. Pi over 18, what I'll do is we'll just give it a general figure because these, let's see, it's 1, 2, 3. Can I get pi over 18 out of this? Let me quickly see. That would be 2 if it's 3 units. We can go to 6. It's going to be like a quarter of or half of one of these squares. So what we'll do is we'll just make an estimate of it. The whole thing gets shifted to the left, so it's going to look something like this, following roughly around the same one before. It would just continue down. The green one would be our final answer to this one down here. Okay. With that being said, let's use the same information for cos. Now what's different about cos is that cos, if we were to write the original cos x, has different starting values, okay? So 0 and 1 is a value, so that actually happens, we'll say this is 1 and this is 2, 1 and negative 2, okay? We actually start up here. When we get to pi over 2, that's actually at 0, okay? Pi is at negative 1. 3 pi over 2 is at 0 again. And then finally, 2 pi is back at 1. Okay, so these 5 coordinates come in really, really handy for cos. So the original one, we'll give it a bit of a curve to it. But here's your original cos. And again, same as before, we want to look at what this function would look like with our potential variables. So if A cos, if there's a horizontal stretch or compression, is there a horizontal translation or phase shift? Is there a vertical translation to it? So let's get our values out. There is no A, so it's actually the value of 1, so A happens to be 1, which means there's no change. There is a B value here. B happens to be 5, so that's going to make quite a bit of a change to ours. Okay, and then we get a C value, negative pi over 2. So we're going to have a horizontal movement by half to the right. And then finally we have D, which is negative 2. Okay, very quickly, what this means, B, this one being so important, is there are now 5 periods in what it used to be just 1 period. Okay, so pi over 2 used to take us 1. So we divide that, we actually divide that by 5, so we get 2 pi over 5, and that is the new value to when a new period would end. 2 pi over 5 is a little bit less than, since 2.5 pi over 5 would be the equivalent of pi over 2. That means an entire period actually happens within this amount of space, okay? It's not exact because of kind of the graph they've given us. But our new phase shift here, we're going to go all the way down to 1 and then back up in under a half. And then again in under a half, in under a half, under a half, and then back up again. So we now have 5 periods within what used to be our old one. So we've kind of checked off B. C is phase shift to negative a half. So we take all of these and we're going to shift them to the left about a half a unit, which if they were 2 pi over 5, they'd overlap perfectly, but they don't, which means it's just going to be slightly off the original. So I'm going to give it just a rough estimate here. It's going to look something like that. Very, very close. That last one wasn't so close. There we go. This is why we use a lot of times graphing calculators. It makes it much simpler to do these kinds of phase shifts. And then finally, the very last thing is it's going to go down 2 units. So everything is going to move down 2. In fact, this will be down here at negative 3. So you're going to get something that looks, I'll try to duplicate the blue. The middle is at 0, so now the middle is here at 2. This is going to be at 1. So we're looking at something that looks like this. 4, 5. So there's our new wave of this function here. Okay, we'll zoom back out a little to see the final product of this.